Section 1.1.3 Learning Rules and Representations from Data. To define deep learning and understand the difference between deep learning and other machine learning approaches, first we need some idea of what machine learning algorithms do. We just stated that machine learning discovers rules for executing a data processing task, given examples of what is expected. So, to do machine learning, we need three things. Input data points. For instance, if the task is speech recognition, these data points could be sound files of people speaking. If the task is image tagging, they could be pictures. Examples of the expected output. In a speech recognition task, these could be human-generated transcripts of sound files. In an image task, expected outputs could be tags such as dog, cat, and so on. A way to measure whether the algorithm is doing a good job. This is necessary in order to determine the distance between the algorithm's current output and its expected output. The measurement is used as a feedback signal to adjust the way the algorithm works. This adjustment step is what we call learning. A machine learning model transforms its input data into meaningful outputs, a process that is learned from exposure to known examples of inputs and outputs. Therefore, the central problem in machine learning and deep learning is to meaningfully transform data. In other words, to learn useful representations of the input data at hand, representations that get us closer to the expected output. Before we go any further, what's a representation? At its core, it's a different way to look at data, to represent or encode data. For instance, a color image can be encoded in the RGB format, red, green, blue, or the HSV format, hue, saturation, value. These are two different representations of the same data. Some tasks that may be difficult with one representation can become easy with another. For example, the task select all red pixels in this image is simpler in the RGB format, whereas make the image less saturated is simpler in the HSV format. Machine learning models are all about finding appropriate representations for their input data, transformations of the data that make it more amenable to the task at hand. Let's make this concrete. Consider an x-axis, a y-axis, and some points represented by their coordinates in the x-y system, as shown in Figure 1.3. As you can see, we have a few white points and a few black points. Let's say we want to develop an algorithm that can take the coordinates, x, y, of a point and output whether that point is likely to be black or to be white. In this case, the inputs are the coordinates of our points. The expected outputs are the colors of our points. A way to measure whether our algorithm is doing a good job could be, for instance, the percentage of points that are being correctly classified. What we need here is a new representation of our data that cleanly separates the white points from the black points. One transformation we could use among many other possibilities would be a coordinate change illustrated in Figure 1.4. In this new coordinate system, the coordinates of our points can be said to be a new representation of our data. And it's a good one. With this representation, the black-white classification problem can be expressed as a simple rule. Black points are such that x is greater than 0, or white points are such that x is less than 0. This new representation, combined with this simple rule, neatly solves the classification problem. In this case, we defined the coordinate change by hand. We used our human intelligence to come up with our own appropriate representation of the data. This is fine for such an extremely simple problem. But could you do the same if the task were to classify image of handwritten digits? Could you write down explicit, computer-executable image transformations that would illuminate the difference between a 6 and an 8, between a 1 and a 7, across all kinds of different handwriting? This is possible to an extent. Rules based on representations of digits, such as number of closed loops or vertical and horizontal pixel histograms, can do a decent job of telling apart handwritten digits. But finding such useful representations by hand is hard work, and, as you can imagine, the resulting rule-based system is brittle, a nightmare to maintain. Every time you come across a new example of handwriting that breaks your carefully thought out rules, you will have to add new data transformations and new rules, while taking into account their interaction with every previous rule. You're probably thinking, if this process is so painful, could we automate it? What if we tried systematically searching for different sets of automatically generated representations of the data and rules based on them, identifying good ones by using as feedback the percentage of digits being correctly classified in some development data set? We would then be doing machine learning. Learning, in the context of machine learning, describes an automatic search process for data transformations that produce useful representations of some data, guided by some feedback signal. Representations that are amiable to simpler rules solving the task at hand. These transformations can be coordinate changes, like in our 2D coordinates classification example, or taking a histogram of pixels and counting loops, like in our digits classification example. But they could also be linear projections, translations, nonlinear operations, such as select all points such that x is greater than 0, and so on. Machine learning algorithms aren't usually creative in finding these transformations. They're merely searching through a predefined set of operations called a hypothesis space. For instance, the space of all possible coordinate changes would be our hypothesis space in the 2D coordinates classification example. So that's what machine learning is, concisely searching for useful representations and rules over some input data within a predefined space of possibilities using guidance from a feedback signal. This simple idea allows for solving a remarkably broad range of intellectual tasks, from speech recognition to autonomous driving. Now that you understand what we mean by learning, let's take a look at what makes deep learning special. Section 1.1.4. The deep in deep learning. Deep learning is a specific subset of machine learning, a new take on learning representations from data that puts an emphasis on learning successive layers of increasingly meaningful representations. The deep in deep learning isn't a reference to any kind of deeper understanding achieved by the approach. Rather, it stands for the idea of successive layers of representations. How many layers contribute to a model of the data is called the depth of the model. Other appropriate names for the field could have been layered representations learning or hierarchical representations learning. Modern deep learning often involves tens or even hundreds of successive layers of representations, and they're all learned automatically from exposure to training data. Meanwhile, other approaches to machine learning tend to focus on learning only one or two layers of representation of the data. Say, taking a pixel histogram and then applying a classification rule. Hence, they're sometimes called shallow learning. In deep learning, these layered representations are learned via models called neural networks, structured in literal layers stacked on top of each other. The term neural network refers to neurobiology. But although some of the central concepts in deep learning were developed in part by drawing inspiration from our understanding of the brain, in particular the visual cortex, deep learning models are not models of the brain. There's no evidence that the brain implements anything like the learning mechanisms used in modern deep learning models. You may come across pop science articles proclaiming that deep learning works like the brain or was modeled after the brain, but that isn't the case. It would be confusing and counterproductive for newcomers to the field to think of deep learning as being in any way related to neurobiology. You don't need that shroud of, just like our minds, mystique and mystery. And you may as well forget anything you may have read about hypothetical links between deep learning and biology. For our purposes, deep learning is a mathematical framework for learning representations from data. What do the representations learned by a deep learning algorithm look like? Let's examine how a network several layers deep, see Figure 1.5, transforms an image of a digit in order to recognize what digit it is. As you can see in Figure 1.6, the network transforms the digit image into representations that are increasingly different from the original image and increasingly informative about the final result. You can think of a deep network as a multi-stage information distillation process where information goes through successive filters and comes out increasingly purified, that is, useful with regard to some task. So that's what deep learning is, technically, a multi-stage way to learn data representations. It's a simple idea, but as it turns out, very simple mechanisms, sufficiently scaled, can end up looking like magic.